Welcome back to part 2. So what do we get here for the, first off, which one's going to be oxidized, which one's going to be reduced? Okay, how do you know that they're both negative? It's less negative. It's the more positive one, right? So this one is getting reduced. This one's going to get oxidized.
Could you also tell that from the formula? Or
No, because it doesn't tell you the direction of electron flow. It doesn't tell you which one's dissolving, which one's precipitating out.
Okay, but like since the oxidation state on M is +2.
And zinc's +2.
Okay, that makes sense.
But I mean, the charge doesn't matter whether it's +2 or +3. That's not going to affect the cell potential. Okay, it's all just got to be this. And even though they're both negative, this one is less negative, more positive, so it's the one that's going to be reduced. Okay, so when we go to write the net ionic equation then, what's reacting with what?
CD2+.
CD2+ plus
zinc solid.
zinc solid. The oxidation is always going to go the opposite direction. And that's going to make CD solid and then Zn2+ aqueous. Now, because it's +2 and +2, do we have to balance it anyway? No. But if this was, let's just say the cadmium, it only has one choice, but let's just say that it was 3+. What would we have to do? That's right, because we have to make the charges balance. Now that's, again, this was +2, so we didn't have to do this. I'm just saying what if, okay? What if, just so we know that, because a lot of times they'll say write the balanced net ionic equation for the reaction. All right, so let's go back to what it really is. 2+. Okay? So now, write the net ionic equation and calculate the cell potential. E cell is going to equal E red, -0.403 minus the -0.763 is going to equal 0.333. Oh yeah, 363. 360. Okay, so that's all B. So how do we do D? Pardon me, C. Delta G is equal to what? Fe, which is going to be negative, what's N? 2. Does everybody know how to get in? Okay, because nobody really just kind of threw out the answer there. Times 96,485 times 0.36. And again, what did I tell you? What are the units going to be on this? Joules per mole, not kilojoules. What does that come out to in terms of joules? Okay, say it one more time. 469? That's joules, so we have really 3 sig figs here. So the kilojoules, 3 sig figs, this is going to be what? -69.5 kilojoules per mole. And then lastly, D. What's different about D?
Not standard condition.
Not standard conditions, so what equation do we have to use?
The one from yesterday.
The one from yesterday, the Nernst equation, N-E-R-N-S-T, the Nernst equation, okay? Which is E is equal to E cell minus 0.0592 over N times the log of Q. So that equals 0.36 minus 0.0592 divided by 2 times the log of products. This zinc 2 plus is the product. It's 0.1 molar divided by the reactant, which remains unchanged, which is 1 molar. And what does this come out to? Loud enough for me to hear. 0.656. Do we agree? No. 0.390. All right, Nathan, think out what you did wrong in the calculator. .390 volts. Okay, so we can kind of go through. Notice how this one has an electrolysis problem in it. It's got a voltaic cell, E, right, just the net ionic equation. Calculate your E cell, delta G, and then a Nernst equation. And so it kind of gets all the buttons in one problem. Now we have these two equations right here. Delta G is negative RT natural log K. Delta G is equal to negative NFE. There's probably an equation that relates E to K, but I would just use these two. If you need to calculate, like one problem says calculate the constant K, but they had just said you calculate delta G. Well, then delta G is equal to negative RT natural log K. Remember, anytime we have delta G, any of these energy ones, this is 8.31 is the value of R that you use.
Which one is 0.0821?
That's with normal gases. That's liter atmospheres, Kelvin moles. That's when we just PV equals nRT.
Okay, so that R is different from that.
It's the same R, just a different, calculated in different units.
Okay.
It's still the gas law constant. It's just calculated in different units.
Okay.
All right, so turn the sheet over and look at number 90, year 97. I want to let you take a few minutes and see if you can figure this one out. Let's just try to get A and B for right now. A, B, and C. A, B, and C for now. Alright, so write the equation for the reaction that occurs at the anode. Well, what reaction occurs at the anode? Well, what process?
Oxidation.
Oxidation. So we have to figure out which one's being oxidized. But it says in an electrolytic cell, a current of 0.25 amps is passed through a solution of chloride of iron. Okay? So that means it's going to be, now iron can either be +2, but it's going to be FeClX. Okay? But if we know it's iron and chlorine, what's the charge on iron and what's the charge on the chlorine? +2, and then that's the question mark. Well, actually that's not true. This is plus something, and this is -1. That's what we know. Okay? But we know that this is positive. So, which one of these is going to get oxidized? The chlorine. Okay? The Cl- is going to get oxidized to Cl2 plus 2 electrons. And I know that because just the iron chloride, it's going to be positive and negative. The negative thing is going to get oxidized, the positive thing is going to get reduced. Because it's telling me that I'm getting iron solid and chlorine gas. So I know my reaction is Fe solid plus chlorine gas. Now, that doesn't mean that's automatically a 2, because we could balance with coefficients and whatever. But I do know that the iron is going positive. It's iron chloride. It's always the iron metal is going to be the positive thing. The non-metal is going to be the negative thing. That's a positive to 0, negative to 0. This is the one that's getting oxidized. Okay? Now when the cell operates for 2 hours, 0.521 grams of iron is deposited at 1 electrode. Okay? Determine the formula of the chloride. What do we need to know in order to get X? The charge, which is what in our electrolysis, which conversion factor? Which is represented by which letter? N. Okay? Moles of electrons per mole of substance. I need to know how many moles of electrons are being transferred. Okay? Well, when it goes for 2 hours, I'm going to start with time. 2 hours, okay, times 3,600 seconds per hour. Then what? Amps, which is 0.25. Then what? Faraday. 1 mole of electron, 96,000. I do 500 all the time. 485 coulombs. So that tells me how many moles of electrons got transferred, but it's per how much? Okay, so we can get this number. What's this number equal to?
0.0186.
Okay, but we need to know moles of electrons per mole of substance. How can I know mole of substance? Again, we have grams. So it's 0.521 grams of iron times 1 mole over 55.8, 55.85. That equals
0.00933.
933. Okay? Moles of iron. So N is going to equal what over what? And that's gonna equal 2, right? So what's my formula? Because that means it's plus 2, that means 2 electrons are being transferred. So it's going to be FeCl2. So this is one in which we had to calculate N. We need to know N. In order to know the formula, in order to be able to figure out the charge, you have to know what N is. To figure out the molar mass, you have grams per mole. So it's really going to be Fe2 plus then, plus 2 electrons, goes to Fe solid. So what's my overall equation? Write the balanced equation for the overall reaction. What's it going to be? It's right here. Just, what's it going to be?
Fe2
Plus
plus 2 Cl minus
2 Cl minuses goes to Fe
Cl2.
plus Cl2 gas. To figure out the charge, we have to figure out N. Again, N, you have to know that N is moles of electrons divided by moles of substance, so I need to know both of those things. Somehow in the problem, they give me the information to know those two things. But again, if you don't know what you're looking for, you're not going to be able to find it. You need to know what the question's asking for at the beginning. So, whenever you're looking for the charge, you're looking for N. If you're looking for the molar mass, you're looking for grams divided by moles. If you're given time, you're looking for grams, you're given grams, looking for time, you do that whole thing. Now, let's talk about D. How many liters of chlorine gas measured at 25 and 750 millimeters of mercury are produced when the cell operates? What does that sound like? An ideal gas law problem. Okay? So, for D, PV is equal to nRT. We're looking for volume, so volume is equal to nRT over P. Do I know the pressure?
Yes.
750. Do I know the temperature?
Yes.
25. I know R. What don't I know? Moles of chlorine. Okay? Okay, but we're operating here. 0.52 grams of iron is deposited. So in my balanced equation, for every mole of this, how many moles of that come in? What's the coefficient in front of Cl2? 1. It's 1 to 1. Okay? Cl2 is one molecule. So how many moles of iron did we have?
0.00933.
93. So that's how many moles of chlorine got produced. So go ahead and give me an answer then. So we got to do 750 divided by 760. Or you could have used 62.4 for R.
got 0.239.
0.239,
1.
0.231, did somebody else get 0.231? Point 231 liters of chlorine. All right. Let's go ahead and just continue to finish this problem. I'm going to let you guys do it, but I'm going to give you a hint. We have 3 grams per hour is what we want to make the chlorine gas. The question's asking for calculate the current. What units are current in? Amps, which is what units? Coulombs per second. So you got to get grams per hour to coulombs per second. Mishka, work on this problem. Y'all, you need to put your phones away, everybody. You see you guys just text at will in here. And we can't really just do that. So what conversions are we going to have to do on the top? Grams to moles of chlorine to moles of electrons to coulombs. And on the bottom, we just got to take hours to seconds. So we take grams to moles using the molar mass, which is 70.9. Oh, it needs to go on the bottom. 1 mole over 70.9 grams, times, what's N gonna be? 2, we get that from the previous balanced equation. So we have 2 moles of electrons for every 1 mole of chlorine. And then we have 96,485 coulombs for every 1 mole of electrons. Then what do we have to do?
Hours.
So there's 1 hour, it's 3,600 seconds, is equal to so many coulombs per second, which is 2.77? 2.27 amps. And I think amps has a halo on the top. Okay, so all different variations of the problem as far as what we look for. But again, when you're looking for something, what are the units on it? And then what am I given in the problem, and how do I get there? Okay, because again, it's very, very important on these that you know what you're looking for. Because if you just try to start with something, you're just going to get lost. You got to know where you're going. All right. Let's just go back to the front sheet. Let's look at 1991, some thought questions. Oh. Part A. Part A question is kind of a personal question for me. Because back in the 90s when I lived in Baton Rouge, I was working at a small private school, not making hardly any money, broke, newly married. And I was trying to figure out if it was something to do for summer work. And so Dow Chemical is a huge chemical company. And in Louisiana, all up and down the Mississippi River, they got a ton of chemical companies because they have the Mississippi River to transport everything on. So I kind of spearheaded a teacher hire program from Dow Chemical. And they hired 5 to 10 teachers for the summer, just to kind of work side by side and get some experience, real world experience, whatever. So I worked at Dow for a summer, okay? Now, unfortunately, the economy tanked and they cut the program out the next year or whatever, but I got to work one summer. And I worked at the chlor-alkali plant. Now, what do you think gets made at the chlor-alkali plant? Salts, but specifically which elements? An alkali, which means base, and what does that sound like? Chlorine, okay? Now, in Napoleonville, in South Louisiana, they have brine saltwater wells. Does anyone know what that means?
Brine.
What's brine? That's a salt water. So they have saltwater cells, saltwater wells. So they pump in an aqueous solution of sodium chloride. Okay, up into Plaquemine. It's probably about a 50-mile pipeline of salt water. And so they electrolyze that. And that's my non-accepted form of electrolysis, my 2 lightning bolts, and it kind of looks like ZZ Top, okay? The IUPAC, International Union of Pure and Applied Chemistry, will not recognize this as a legitimate sign, okay? But that's my electricity. Now, normally, we just read on the previous problem we did that we get sodium, metal, and chlorine gas. But when you have aqueous, NaCl, and water, we really have NaCl and we have water. So now we have 2 positive things and 2 negative things that are going to battle for the electrons. And so the electrons are always going to take the route of least resistance. So it turns out that when this happens, the Na plus does not get reduced. The hydrogen is the one that gets reduced, so I really should write it down here. The sodium stays, but the hydrogen gets reduced to hydrogen gas. So hydrogen gas bubbles at one electrode. They collect that hydrogen gas and then they sell it to another company that they're in conjunction with called Air Products, which is, by the way, where I buy, there's a branch of it in Pelham, which is where I buy the liquid nitrogen that we do demos with, okay? But then the Cl- and the OH- are both competing to be oxidized. Well, the Cl- is what gets oxidized into chlorine gas. So chlorine collects at the other electrode, and then the OH- just stays in solution. So when the reaction's all said and done, hydrogen gas is collected at one electrode, chlorine gas is collected at the other electrode. They're bubbling up and out of the solution. The chlorine then is sent to different, Dow is making plastics, so they send it to the plastic plant because, remember, PVC, does anybody remember what PVC stands for? Polyvinyl chloride. So they add the chlorine to the plastic to give it hardness. So they use the chlorine right there at the plant to add to the plastics to make PVC. The hydrogen is sold off. That leaves NaOH. Well, they don't want that just to be a waste. So they figured out that they could sell this to like tomato canning companies because they have to treat the inside of the cans with the base, the alkaline, because the acid from the tomato is going to react with metal. So if they treat it with the base, it keeps the acid from dissolving the metal can when it's sitting there on the shelf. So they sell this, but this has to be food grade because it's going to touch something that food goes into. So the FDA has to monitor this, so it has to be super exact, super pure. Well, when it comes out, it's about 8 to 10% NaOH. They're selling it at 50% plus or minus 0.5%. Let me make that point later. So how do they get it from 10% to 50%? How can you get from 10% to 50%? What do you have to do?
Concentration.
No, that would measure the concentration of it. That wouldn't change the concentration of it.
Do what we did with the.
How can you make it more concentrated?
You add more.
Add more, but you don't have more. It's always coming out of this. What's the other way? Instead of adding more,
Take
so what's the other thing that this is in? Water. So what do?
Heat it up.
Heat it up and evaporate the water off. Right? And that's going to make it more concentrated. As the water evaporates off, it's going to get more and more and more concentrated. So they have a very impressive system to where they have a sphere where this NaOH is in, okay, and it's the 8 to 10%, and they begin heating it up. And they begin evaporating the water off. Now this is what the mechanical engineers and the chemical engineers work together to do. And they heat it up to the boiling point and boil it off for just a certain amount of time to get it to another certain percent. And I don't know that it's proprietary information as far as how long they do all that and what the real process is. But they don't get it to 50% right here because it takes a tremendous amount of energy to boil water. So then what they do is after heating it for a little bit, they send it into a bigger, this is at 1 atmosphere. Then they lower the pressure to some lower pressure like 0.75 atmospheres. Well, what does lowering the pressure do to the boiling point? Lowers it. So they use the latent heat. They don't have to add any more heat because it's at 100 degrees right here boiling. And then they let it go into here. And then at the lower pressure, it just flashes off some more of the water because it just boils at the lower pressure. But that cools it off too because boiling, all the high-speed molecules are leaving. So it cools down. So then they go into a third one where it's like 0.5 atmospheres. And they have it timed perfectly to where they know the exact temperature it's coming out. And so again, more flashes off. So when it comes out, it's right at 50% plus or minus 0.5%. And then the line workers have to take a sample every hour or two just to make sure, and then they send it to the lab, which is where I worked, and we test it to make sure it's indeed, and we do a titration, to make sure that it's exactly 50%. Now what's cool is they have a machine that does an auto titration. You just put the sample in there and it automatically titrates and spits out an answer. Okay? But one of the things I had to do was go through and find out, well, are we meeting all the food grade requirements that the FDA has put out so if they get audited? And one of the things I found out, which is what I harp on y'all on, is that the machine spit out a tape with the recording. And then the workers would go and read the tape and record it into a log of, yeah, at such and such a time, we took this sample and it was exactly this percent. Okay? Well, FDA says that little printout is the first set of data. You have to include that printout. Sometimes the guys would do some of the preliminary stuff and write on a paper towel before they put it into a log. Well, paper towel had to be stapled to the log sheet, and they did not like that. Okay? I was not a real popular person because I was changing up their system that they've been doing for a long time. Okay? Probably why I didn't get hired back. But the FDA says that whatever you record the data on first, that's your primary source, that's the one you gotta keep. Okay, because you could transpose numbers, you could make mistakes every time you recopy it. So, this is called the chloralkali process. If you put any alkaline metal with any halogen, you're gonna get hydrogen gas, the halogen gas, and then the alkaline metal ion hydroxide, the base.
Oh, so you start out with like one CL and then NaCl?
Yeah, it's not balanced. We have to balance the half reactions and just kind of go through it. But it does balance. Okay, so if you have pure salt, it just goes to sodium, metal, and chlorine gas. But if you have an aqueous solution, instead of, you have two things competing to be reduced and two things competing to be oxidized, only one wins. They don't both get oxidized, both reduced. The electrons go with the least resistance, and this is the one that's the least resistance.
Is there a way to like know which one you get oxidized or reduced?
Well, generally, the one with the greatest reduction potential is the one that's going to get reduced. And the one with the lowest reduction potential, what is going to have the greatest oxidation potential, is the one that get oxidized. However, there's a complicated thing called overvoltage, which actually occurs here, where the reality is I think the hydrogen is, I don't know, but for some reason or other, there's something else complicated that causes the hydrogen to be the one to be reduced instead of the sodium. Oh, that's beyond the scope. I've read about it, but I can't remember it. All right, so, question A, when an aqueous solution of NaCl is electrolyzed, chlorine is produced, but no sodium. Because what's going to be produced at the cathode instead?
H2.
Hydrogen gas from the water.
Is that?
All right, so the mass of iron produced when 1 Faraday is used to reduce a solution of FeSO4 is 1.5 times the mass of Fe solid produced when 1 Faraday is used to reduce FeCl3. Somebody tell me why that is.
Because more moles of electrons are being transferred.
In
FeCl3.
FeCl3 takes 3 moles of electrons per mole of Fe, whereas FeCl2 takes only 2 moles of electrons. So that's 3 to 2, 1.5 times more. So now when it says the cell that utilized the reaction above has a higher potential when zinc is decreased, okay, but a lower potential when lead is decreased. Why is that? What equation? That's Q, right? The Nernst equation. Okay, so if you increase this concentration, Q is going to be increased, which means it's going to subtract, whereas this one, and again, this is where it's easier to think with Shelly's principle. Now wait on, don't I have 1 minute? Okay? Because I want to look at here. The cell, same cell, if we're doing 1 molar and 1 molar, we get the same voltage as if we use 0.1 molar and 0.1 molar. Okay? Because the log of Q, 1 over 1, 0.1 over 0.1 is going to be the same value, right? It's going to be 1, which is 0, which means it's just E cell. What's going to be the difference between those two batteries? Not necessarily how strong, the same voltage. How long they last, how much they have, how many electrons they can deliver before they go reach equilibrium and go dead. That's the difference again between a AAA, AA, C, and D battery. They all have the exact same stuff, just different amounts, so they can deliver, the big ones can deliver more electrons and drive the bigger equipment that requires more electrons, more current. Good stuff, all right.